Our next presenter is Sage Weil. Sage is the founder and chief architect of Ceph, a distributed storage platform. He was also the creator of WebRing, a co-founder of the Los Angeles-based hosting company DreamHosts, and the founder and CTO of InkTank. Sage now works for Red Hat as the chief architect of the Ceph project. Sage.
Thank you. Can everyone hear me okay? All right, my name is Ceph, and my name is Sage. I work for Red Hat. I'm working on Ceph. Today I'm going to talk about a new storage backend that we wrote for Ceph over the past couple of years. This is a longer talk that's been adapted down to be shorter, so there might be some extra detail in the slides, but I'll hopefully it'll work out okay.
Can't hear you.
Louder, okay. All right, let's see how this goes. All right. Let's see if the slides advance works. And this doesn't work. And that doesn't work. Okay, so a bit of an outline about what I'm going to talk about. I'll give a little bit of background about Ceph, what it is and how it works, and what the backend actually is. I'm going to talk about FILESTORE, which is our old backend based on a POSIX file system on XFS, and why that was problematic. I'll talk about BlueStore, the new backend, and why it's so much better. I'll show some performance numbers, talk about some challenges and our current status, and then I'll wrap up. So first, a little bit of motivation. Ceph is a distributed object, block, and file storage system, all in one cluster. It's designed so that it scales out horizontally with no single points of failure. It's hardware agnostic. It runs on commodity hardware. It's meant to be self-managing wherever possible. And most importantly, it's completely free and open source software. Traditionally, we've always talked about Ceph as being a scalable, high-performance distributed file system, and we always talked about sort of the three goals being performance, reliability, and scalability. Turns out the performance has been sort of a bit of a challenge for much of that time, and much of that is due to this back end that I'm going to talk about today. We just released our latest version of Ceph, Luminous, a couple of weeks ago, and sort of the two key highlight features are erasure coding support for the block, object, and file interfaces. Previously, we only had it for object. And the second sort of feature is BlueStore, which is this new backend. And the two go hand in hand, as I'll talk about. So Ceph is built upon a distributed object store called Rados, which sort of underpins the entire system. This is the part that makes sure that your data is spread across all of your storage devices. It makes sure that when something fails, you detect it, and you re-replicate the data, and you heal, and you do all that good stuff. And then on top of that sort of internal object storage interface, we build a number of different access interfaces. There's an S3 Swift gateway called Rados Gateway. There's RBD, which is a virtual disk block device that does snapshots and cloning and multi-site asynchronous replication and all that good stuff that you use for private clouds mostly. And then there's XFS, which is a distributed POSIX file system. But all of those are layered on top of Rados, which is the bit that actually stores all of the data in the cluster. That Rados cluster is composed mostly of OSDs. These are object storage daemons that sit on a number of hosts. Typically, or traditionally, we would have an object storage daemon sitting on top of a local file system, XFS, and that would sit on top of your raw storage device, disk. In reality, it's a little bit more complicated than this. There's a bit of the OSD that's called FILESTORE, which is the module that's responsible for dealing with all that local storage on the local device. And so it hides all the details of how we're actually writing data into XFS. And it turns out that this has been sort of one of our key challenges in the past. And partly it's because of sort of the history that we took, the way that Ceph was designed and how we got to the current point. So in the beginning, we didn't actually use XFS at all, or a file system. We wrote a specialized file system called EBOS, an extent-based object file system. This was an entirely user-based file system that was optimized and designed specifically for storing objects with the workloads that we expected to see. So EBOS used a raw block device. It had a copy and write B tree, and it stored objects, which are sort of like files. And then it had a custom interface that it exposed to the rest of the Ceph OSD. And then we had a second implementation of this abstract interface called FAKESTORE that we used just for development. It would store objects as files, and we use it on our laptops when we were developing. But EBOS was sort of the thing that was meant to store all the data in Ceph. That interface we internally called OBJECTSTORE. It was the sort of the internal storage interface for storing stuff locally on our locally attached storage device. And the interface is pretty simple. We had objects, which are sort of like files. It's just a lump of data. It's a bunch of bytes. You could associate some attributes with objects. So think small key value pairs like version equals 12. And later on, we added what we called OMAP, which was key value data. So we could store key value data inside an object as sort of this self-contained unit of data in the system. Collections were kind of like directories. It was just a bunch of objects that are grouped together. In reality, objects in Ceph exist in a logical storage pool that's spread across the entire cluster, and a collection was just a shard of that overall pool, a subset of a slice of the namespace. But one of the sort of the key features of this internal interface that evolved because we had control of that lower level object storage system and the thing that was above it, and it was internally transactional, we made that a rich interface so that all the update operations that the Ceph OSD was passing down to this internal module were in the form of transactions. So it would be things like update an object, update its version, and log something saying that we made that update, and that would all be committed atomically on disk. And we had that flexibility because we were building it all ourselves, and it was sort of the most natural thing to solve the problem at the time. Some time went on and we started adding more things to EBOS. Eventually we got to the point where we needed to add data checksumming on disk. And btrfs arrived on the scene, which internally had a very, very similar design to what EBOS was doing. But it was in kernel, it had a whole community around it. It looked like it was going to be the future of Linux file systems. And so we said, hey, we should just use btrfs, hook into their internal transactions, stop maintaining our own special thing that was just for Ceph, and we can save ourselves a bunch of time and effort and focus on the other parts of Ceph about replicating things across nodes and so on. So we did that for a while. It turns out that exposing POSIX transactions into USERSPACE just was a bad idea. You could give a whole talk about why that's the case, but trust me, it's a bad idea. Later, we pivoted to using XFS instead of btrfs when we were finally rolling Ceph into production behind OpenStack clouds. So we sort of shifted back away from EBOS, leveraging POSIX file systems. And to do that, we took that fake store, that sort of toy implementation of the interface just for doing development, and we renamed it FILESTORE, and we made it do all the things that it had to do. So it would store objects and files in POSIX. The collections became directories. So the kind of directory layout and structure on disk that you would expect. We added in level DB in order to store some additional metadata and to store that key value data that we have. It turns out that every single Linux file system has its own sort of unique special limits on the size of XAdders and how many XAdders you can cram into a single inode. And so we also have a bunch of hackery to sort of spill over large XAdders into level DB when necessary. But overall, it kind of worked. But emphasis, I guess, is on kind of. So there are sort of a number of big challenges that came up when we were trying to sort of shoehorn our nice transactional interface that was natural for Ceph OSDs onto a POSIX file system. And the first one is transactions. We had a transactional interface. It made the rest of Ceph's design so much better and easier, but it didn't really map onto file systems. So most transactions in Ceph are pretty simple. It's something like, write this little bit to a file, update the XAdder on the file saying that the version is now n+1, and insert a log entry into the log saying I touched this object. And those logs are important for doing recovery efficiently, so we know exactly what things have changed and which versions are where and so on. But transactions can actually be very complex, so that's just the simplest case. But doing that on POSIX doesn't really work. POSIX doesn't provide any kind of transactional interface. So we did sort of the simplest thing, which is basically just to take the entire transaction description, including the write and all the updates, serialize it into a bunch of bytes, write it to a write-ahead journal, commit that to disk, and then write it back to the file system. And that gave us the atomicity we needed so that if we crashed, we could always replay the journal, and we could always leave the store in a totally consistent state. But that means every write in Ceph was written twice. We wrote it to the journal, and then we wrote it to the file system. So that was inefficient. And also, it was just gross. There are some operations that are sort of non-idempotent, like things like rename that have a read side and a write side. And so there was a lot of ugly hacks to make sure that if you replayed this journal, you would always get the right result after the whole thing was replayed. So it was frustrating. The other challenge was the kernel cache. So in general, kernel caches are wonderful. File systems in Linux all share the page cache and inode cache. It's all magically managed for you. It'll use all the available memory in the system if it can. As soon as there's memory pressure, it'll sort of free things. It's great. You don't have to think about it. It's fast. It's very highly performant. The problem is that when you take that and you combine it with write-ahead logging, things suddenly suck again. So we do a lot of read, modify, write operations and stuff where we look at the state, we make a change, and then we update it. But because writes have to go through a journal before they're applied to the file system, you literally have to wait for the previous transaction to commit, be applied to the file system before you can read its effects and prepare the next transaction and then write again. So you end up either serializing updates based on your journal and the number, however many IFs you can get out of your slow hard disk, or you have to re-implement another sort of cache in your own that's just managing or keeping track of in-flight writes, so you avoid this sort of annoying serialization. So that was frustrating. But the last and probably one of the biggest problems is problems with enumeration. So the way that Ceph takes all of its objects and distributes them across the cluster is it hashes the name, and it sort of takes that 32-bit hash value, and that defines a well-defined sort order of all objects in the system, and it shards that namespace into pieces and distributes them to certain nodes. So when we do enumeration of the objects in Ceph for like scrubbing, for consistency checks, or enumerating objects in order to replicate them across to other nodes, we have to have this well-defined order for everything to work. But POSIX reader does not give you ordered results. It's sort of randomly whatever the file system happens to implement with its internal hashing and B trees and whatever else. We also have this need to take an existing shard as the data set grows and split it into pieces, and so we can sort of redistribute it across the cluster. And when we're storing these groups and directories, we have to literally take a bunch of files and copy them to other directories in order to split them in pieces. And so POSIX didn't really give us the right tools for the job. In order to make this work, the FILESTORE backend would basically take all of the objects in a collection and it would hash directories based on that sort of a prefix of the hash. So as soon as a directory got bigger than some threshold, it would split it into pieces based on some hash prefix, and if the directories ever got small again, they would get sort of merged back into the parent. And then whenever we wanted to do enumeration, we can list all the files in a directory, which hopefully is bounded to be some small number, sort them in memory, and then give back an ordered result. So it worked, but it was gross, and you had all this extra directory renames. It sort of wreaked havoc on XFS's allocation group hints about trying to keep things in the same directory close to each other. It just messed everything up, and it was pretty slow. And the headaches sort of continued. So as you were populating a cluster and putting billions of objects into the cluster, all the nodes in the cluster would sort of hit these split thresholds at the same time and start splitting directories into pieces, and throughput would totally tank as all of them did that at the same time. It turns out that we want consistent performance, and so when we're writing things into XFS, we want to bound the amount of sort of deferred write-back work that's going to happen. We can push things to disk with fsync, but we can't control the number of inodes that are sort of dirty in the XFS journal, and eventually those need to get written back to the XFS internal B trees, and we can't control when that happens or how many of them there are. Our QoS efforts were thwarted because we couldn't really control the depth of queues. And when we do snapshots in XFS, we have to clone objects. XFS didn't have an efficient clone operation, and so we'd literally be copying objects and have this sort of latency spike. We came to the realization that XFS was just the wrong tool for the job. We had a very different storage interface that we wanted to implement, and putting it on POSIX was not the right answer. And so a couple years ago, we sort of started experimenting with new custom backends. NewStore was an attempt to take just all the metadata about objects and put it in LevelDB, but still store the data in files. That helped, but still sort of ran afoul of some of the same issues in the POSIX interface. And eventually we said, forget this, we're going to write a completely fresh backend, again, sitting on a block device, and we called it BlueStore. So BlueStore is sort of a block version of NewStore, where we're consuming raw block devices. We leverage an existing key value database, RocksDB in our case, for storing the metadata, so we don't have to sort of rewrite everything from scratch. Data is written straight to the block device. We have pluggable inline compression, full data checksums. And the goal with this is to target sort of the current generation of devices. So hard disks, sort of regular SSDs and NVMe devices that you have out in the wild today. The key challenge in this was how to figure out how to make BlueStore share the underlying block device with RocksDB. So RocksDB is a LSM tree key value database that's very popular, but it uses files to store all of its state, and we don't have a file system anymore. We're sitting directly on a block device. And so what we did is we created a custom backend for RocksDB called BlueFS. BlueFS is a super simple file system. And calling it a file system is generous because we implemented the bare minimum necessary to support just what RocksDB does. It turns out that the LevelDB and RocksDB developers did a really good thing in abstracting out all of the operating system dependencies. So all the file operations are already abstracted behind this env interface, so we just had to implement a class, excuse me, and we could slot in all the right file operations to back RocksDB. So BlueFS is super simple. Its on-disk layout is super simple. We have a super block and we have a journal. All the metadata lives in the journal. When we update things, we write it to the journal. When we mount, we just read the entire journal and read all the metadata into RAM. There's no other metadata structures on disk. And then when the journal gets too big, we just sort of rewrite a new journal that has just the metadata that's still accurate. So periodically we compact it. But it turns out that RocksDB writes big files, so we can keep everything in RAM. Periodically compacting it is like totally sufficient for our needs. The only sort of clever thing we did is we configured RocksDB so that it wrote different types of files into different quote-unquote directories. So its write-ahead log, its WAL files were in one directory, and its database files were in another. And then BlueFS would look at the file name, and it would map that data to different devices. So we could put the RocksDB journal on like a fast NVMe or NVDIM or something like that, and the rest of the data would go on disk. But aside from that, BlueFS was like just as complicated as it needed to be. And that solved our problem. So a little bit about how BlueStore would store its metadata. I'm going to go through these pretty quickly because it's probably not super interesting about exactly how BlueStore works, but mostly that you can write something that's not too complicated to solve your problems. So the main metadata structure in BlueStore is an O-node. This is like an object or a file. It lives in a single key value pair in RocksDB. And it has just a little bit of metadata, how big the object is, what its attributes are, and information about how the extents are stored on disk. I'll talk about that in a moment. The collections, as I mentioned, are sort of this shard, a slice of the overall object namespace. But we constructed the key names for all of our objects so that they sort in the same order that they logically sort in Ceph. And so the collection is really just a description of what the current sharding is and which ranges are mapped to which shards. And so when we split, in order to do resharding and to redistribute data, all we do is we change that description, but we don't have to actually rewrite any other metadata because they're already sorted in order in the tree. So this gives us nice ordered enumeration and efficient splits. A blob is metadata about some data that's on disk. So it's which extents they're stored on a block device, all the checksums for that data on disk, and if it's compressed, information about the compression, the compressed size versus uncompressed size. Every once in a while, or sometimes objects get cloned in Ceph, and so there are actually multiple objects pointing to the same bytes on disk. In that case, we need some additional reference counts on those extents before we release them, and so there's also a shared blob structure that handles just the reference counts. And then the extent map is the bit that sort of glues together the objects and the blobs. So it's just mapping bytes in the object to which blobs and which bytes are sort of referenced by those objects. We normally sort of serialize it in chunks, so we have which extents and which blobs. If it's a small object, then we can cram it all into one key value pair and stick it right with the O-node in one slot in LevelDB or in RocksDB, so it's nice and efficient. But if you have a big object or an object that's fragmented or have lots of different small writes or something like that, then that might be a pretty big map, and so we shard it into pieces so that we can spread it across multiple key value pairs and limit the size of our updates and so on. And there are a few corner cases to deal with. If a sharding boundary crosses a blob, then we have to store the blob in a different place and some other details, but those are the basics. The data path also is relatively straightforward. So again, our interface is transactional, so we have information about what transactions are in flight. That's a trans context. And because we have sharded the namespace into collections, each collection has an independent sequence of transactions that are ordered within that collection, but not with respect to each other. So we have lots of parallel queues of events that are ordered, but no sharing between them. So BlueStore is free to sort of schedule things as it sees fit. And then when we write data, we do it in sort of a write anywhere, copy and write fashion. So if the write is large enough above our allocation size, we'll allocate new space on disk and just write it to new space. Once that commits, then we can write the metadata transaction that references it. In some cases, there's a blob that wasn't completely written. There are parts of it that sort of are still unused, and so we can write into an existing blob. It's an unused region, and there's no other references to this block, so we're not clobbering any existing data. But then the third case is when we have a small write that's sort of overwriting existing data. And in that case, we can't overwrite the existing data because if we crash at the wrong point, then we'll corrupt the previous state and not have committed the new state. And so in that case, we put the data that we're writing in the journal event. So the transaction says, this is the update, and this is the write that I'm going to do later. So it's like data equals journal in ext4 or something like that. And then after that commits, then we asynchronously apply that write to the system. Those are called deferred writes. We don't have a kernel file system anymore, so we have to implement our own cache. That was a bit more work, but it turns out to be better in the end. So we have cached nodes for each collection. They're all independent, so we don't have any false sharing. Blobs can have data buffers cached as well. We always have to track in-flight writes so that we can sort of read the effects before they commit. But we can also cache things on disk if we think we're going to read them again later. And then both the buffers and the nodes are linked to a structure that we call a cache. That's basically a big LRU so that we can handle cache trimming. We implemented a 2Q, actually, so it's resistant to invalidation due to a sweep. But the main sort of trick we did here is that we sharded the cache for parallelism. Ceph OSDs already have sharded work queues for all of their requests. So they allocate different placement groups to different queues so we can utilize multiple cores and they don't share between them. We mirror that exact same sharding scheme in BlueStore, and we match that with the caches so that the CPU are the cores already have an affinity to the cache structures, and we don't have cache lines ping-ponging between cores and so on. And that's sort of the BlueStore design in a nutshell. So did it all work? We'll look at some performance numbers here. I apologize, some of these graphs are pretty old. They're from a talk I gave last spring. But they reflect sort of the same state of affairs. The only sort of confusing bit here is that this is showing FILESTORE, BlueStore, and a couple other development versions. The lines to pay attention to are the red line, which is the BlueStore, which most closely resembles what we have today. And confusingly, the blue line is FILESTORE, the old thing. So just keep that in mind. The top graph is throughput. So the first thing to notice here is that for large writes, when we're writing 4 megabytes at a time, we're basically essentially twice as fast as FILESTORE. And that's because we're avoiding this double write. We don't have to write the data to the journal and then apply it to the file system, but we can just write it straight to where it's going to go and update the metadata. On the bottom graph is the exact same data, but shown in terms of IOPS. So you can also see that for small writes, we're also about twice as fast. And that's just because we're avoiding all the machinery of the file system that's not quite adapted to what we want to do here. The interesting bit is that huge knee where it jumps up at between 32 and 64K, and that's because of the allocation size threshold. So writes at 64K or above, when we submit a write, it's just allocating a new extent on disk and writing it to a new spot on disk. And so when you have lots of writes coming in, it's just sort of streaming all these things out. It's nice and fast. Whereas once we drop below that threshold, it switches into the deferred write mode where it's journaling the update into the journal and then asynchronously overwriting the existing data on disk. And this is really just a trade-off between performance and fragmentation in the future. So you can adjust that up and down. The main thing that we did after these tests were done is we changed the way that deferred writes were handled. So we batched them up in memory much better, and so that we can write them out more efficiently. So that line has moved up a bit. But that's where that comes from. Sequential writes are similar. Again, for large writes, it's indistinguishable for random writes, so it's much faster. On small writes, though, we had sort of an annoying, confusing result where we showed that we're actually much slower than FILESTORE for sequential writes. And it turns out that the reason was because of the way that these deferred writes are being handled. With FILESTORE, we would write them to the journal, and then we would write them to the file system. But XFS was allowed to sort of accumulate a lot of writes in cache before it actually wrote them out. And so it would batch them up and turn them, a bunch of sequential writes into one big sequential I/O. Whereas this version of BlueStore was actually dispatching them as soon as they committed. So we had sequential I/Os, but they would be spaced apart in time and they'd be interleaved with journal updates, which is very inefficient. So the deferred write batching that I just talked about that we implemented since then has brought this line much higher and above where FILESTORE was. So that's hard drives and sort of normal I/O. It turns out that the way that BlueStore manages metadata also made a big difference on performance. So these tests are for the S3 interface, which is writing objects through the Rados gateway into Rados on top of a cluster with both hard disks and NVMEs for the journal and using erasure coding. The blue and red, the small bars are FILESTORE, and the yellow and green are for BlueStore. And the main thing to take away here is that we're anywhere from 2 times to 5 times as fast as FILESTORE, and that the amount of spread tends to vary based on the level of sharding between buckets. So the way that the Rados gateway works, it's maintaining an index for each bucket, each S3 bucket, so that you can do things like enumerating objects and applying quotas and so on. And it's a read, modify, write operation on those indexes. So depending on the level of sharding, you may or may not be bottlenecking on the updates, the serialized updates on those indexes with FILESTORE. And with BlueStore, we don't have this annoying issue where you have to wait for the write to commit before you can read the effects and do another read, modify, write. So we eliminated that problem, and life is much, much better. It turns out that sort of the other big feature in Ceph Luminous that I mentioned, these erasure code overwrites, also allowed us to do things that we couldn't really do before. So erasure code overwrites in general are hard because you have to do a 2-phase commit. You can't you have to make sure that when you're overwriting part of a stripe, you either roll all the way forward or all the way back, because if you have half the updates apply and then you crash, you sort of can't read the old data or the new data. That's why EC updates are hard in general. And so when we implemented this, the OSD basically is cloning the regions that we're about to overwrite with a temporary rollback object, so that if we somehow fail to proceed, we can always roll back. In BlueStore, it's all copy and write internally. You can do this very easily and naturally. But with FILESTORE, POSIX doesn't give us these sort of copy and write semantics. It literally has to read the data and write it to a temporary file and then overwrite the data to commit it. And so the performance is sort of predictably terrible. These graphs are comparing IOPS from a replicated pool versus a couple different erasure codes. So on the left side, you have BlueStore. So the EC overwrites are slower than replicas because there's additional overheads and we're doing this 2-phase commit and some extra work. But it's usable. But when you look at FILESTORE, it's like literally unusable because it's so slow. We just don't allow you basically to use this new feature if you're using the old backend. And part of the reason why we waited so long to implement these overwrites was because there wasn't really a good way to do them efficiently with the backend that we had on hand. Now that we've sort of reclaimed control of our entire storage stack and we can implement the functionality that we need for Ceph in the backend, then we can implement the features in the natural way and without sort of fighting with this impedance mismatch between what POSIX gives us and what Ceph needs. There's some other challenges that are worth mentioning. We moved all of our caching into USERSPACE. We can't just rely on all the magic stuff that the kernel is doing. So we had to do some extra work to make that work properly. One of those things was building a mempool infrastructure that allows us to easily account for allocations. So we can easily annotate types, like STL types in particular, in Ceph as being belonging to a particular mempool. And then we can look at how much memory is being allocated. And we can use this to basically to first of all observe how much memory we have consumed by our cache, and then control pruning of the cache based on actual memory that's being used. And as a bonus, we have some debug options that let us also tell which specific allocations are being done, so we can tell what's going on. Sort of the big downside, though, is that suddenly the cache size is a configuration thing that the administrator has to decide. You have to actually tell the OSD how much memory it should consume for its cache. Before, the kernel would just magically use all memory, and now we have to decide how much we're going to use. So that's sort of the main gotcha. And as a bonus, we can finally have a sane implementation for some of the f-advise hints that we implement. The kernel never did no reuse properly, and sort of a pet peeve of mine, I can finally implement it properly. So that was a bonus. We also have to be very careful about how much memory we used. Previously, all of our allocations were sort of for in-flight IOs, and so it didn't really matter if they were efficient or not. Now we're using gigabytes of RAM, and we want to make sure that we fit as much useful metadata as possible. So we have to pay careful attention to struct packing and so on. Checksums are a little bit tricky. If we use sort of the default 4K granularity for checksums, it's a kilobyte of metadata for every megabyte on disk, which is kind of a lot. But it turns out that BlueStore is able to observe hints on the IOs that it's doing. So if it's Rados Gateway, for example, S3 objects being written that we know are going to be read and written sequentially, then we can do very large checksum block. So we can checksum a 128K block with only 4 bytes. And then you get much better metadata efficiently. The other thing we've had to pay attention to is just sort of naively using all the data types at our disposal, like red-black trees, can wreak havoc on the CPU prefetching, and judicious replacement of some of these data types with, in-memory B trees and so on has had a huge impact on the performance. So we spent a lot of time poring over perf results and so on to make sure that we're doing this efficiently. RocksDB has been sort of a boon and a bane. Mostly it works great and we don't have to think about it, which is awesome. But there are a few sort of issues that we have to pay attention to. Compaction, this background rewriting of the LSM tree SST files into new files. That impact can grow as the overall size of your metadata grows, so we have to keep an eye on that. There's some issues in RocksDB where it invalidates its own cache when it does a compaction that they haven't really addressed yet upstream. So we're sort of pushing them to do that. And also, when it is doing all this compaction stuff is sort of background work, but we don't have a good way to prioritize those IOs when we're actually submitting the kernel through the kernel AIO interface yet. So that's a bit frustrating. We also write a lot of keys that we write and then delete immediately, and RocksDB sort of doesn't realize that and can amplify those to other SSTs, so we're trying to fix that. We hid all of this behind a generic key value interface, so we could swap in a different key value database for RocksDB if we wanted to. But we're open to alternatives, but we haven't really found anything that's as good or better. So for now, we're using RocksDB, but we're hoping someday we'll have a better alternative. So current status, I mentioned that Ceph Luminous was just released a couple weeks ago with BlueStore as both the default and supported storage backend. All the existing clusters out there are still using FILESTORE, and so we have documented methods for basically converting those over to BlueStore. Mostly that just means leveraging the existing Ceph redundancy recovery stuff, so you provision a new BlueStore OSD and delete the FILESTORE one, and all the existing Ceph recovery stuff takes over. And there are some sequences to sort of make that efficient. Our current efforts on BlueStore are mostly around optimization, paying attention to how much CPU time we're spending, trying to optimize the code paths there. It's all sort of working and stable, but it's sort of still early days. This is our first real release, so we have a lot of work to do there. One of the more exciting things being worked on, mostly by the XSky guys, is support for SPDK, which is a kernel bypass library for NVMe. It cuts down the latency as far as bypassing the kernel AIO and some of those context switches, which is nice. But the other thing that SPDK offers is you can prioritize IOs that are being submitted to, which hopefully will help us solve some of the compaction issues. And we have a complete FS check that does a full consistency check, but we're sort of a limited set of inconsistencies that we can repair, so we're sort of making things more robust there. But we have to be careful because Ceph is a distributed system, and mostly if there's a failure, you want to use sort of the existing recovery mechanisms to deal with it. And if there is an inconsistency in an instance of BlueStore, we don't want to somehow repair it incorrectly and let that inconsistency get propagated to other nodes. So we have to be very careful that we understand when we're repairing something that we're actually making it better, not worse. So that's a challenge. Future work, we're talking about tiering, how we can combine hard disks and SSDs behind one BlueStore instance. Unclear whether we should try to implement that functionality within BlueStore or use existing tiering block devices like Bcache or DMCache and then hint RIO so that it can sort of do the right thing. Leaning towards hinting to the block layer so that I won't have to think about it. We've talked a lot about host-managed SMR and things we can do to BlueStore to make it work sort of natively on host-managed devices, but we'll see if that's actually worth pursuing. And then there's also sort of future technologies. So there's persistent memory 3D NAND coming. There are lots of NVMe spec changes with blob stores and key value stores, and so we're keeping an eye on those to figure out how we should best utilize those as we sort of move into the future. So in summary, Ceph is great at scaling out. XFS is great too, but they sort of weren't a match made in heaven, as it were. POSIX is just a poor choice for storing objects for Ceph. So our new BlueStore backend is so much better because it sort of behaves the way it's supposed to behave and we're not sort of fighting against the wrong interfaces. We find that designing our internal storage interfaces without sort of being biased by POSIX was a win. It took us a long time to sort of get here, but finally we can sort of use the interfaces that are natural for Ceph and also implement them the way they are naturally implemented, and we can sort of reap the benefits. But we're not done yet. We're still working on performance and other things. So Thank you very much. This is a picture of the Ceph cluster in my basement. It's a combination of hard disks, SSDs, and NVMEs. It's running the latest Ceph with file system, cache tiering, erasure coding, and of course, BlueStore. And a bonus, it can be administered with untrained IT staff. This is my youngest daughter here swapping an SSD in the cluster. So, thank you very much. I think we have just probably 1 minute for questions, if that.
Any other questions?
Mark.
Have you taken a look at NVMe IO determinism and how that might fit in here and improve performance?
I don't think so. I'm not quite sure what you mean by determinism, but yeah, we've done a fair bit of testing on NVMe, but mostly we're bottlenecked on CPU and other parts of Ceph. So the good news is that BlueStore is fast enough that it's not the slowest part. The bad news is that we have more work to do. So.
Hello. Is the memory consumed the problem? You mean all the metadata is stored in the memory?
It isn't a problem, no. So BlueFS, the backing for RocksDB, loads all its metadata into RAM, but it's a very small amount because it's just information about the RocksDB files, so it's a small amount of RAM. The BlueStore cache that's caching the metadata for all the objects that BlueStore stores is sized however you want it to be. So you decide whether it's 500 megs or 3 gigs, and it'll appropriately cache as much metadata as it can or not. So, yeah.
What specifically led you to evolve from LevelDB to Rocks?
It was mostly just sort of seat of our pants. RocksDB had an active community around it. Lots of people were working on it. Actively developed, whereas LevelDB is kind of deadish, it seemed. So we wanted a responsive upstream so that when we had changes and improvements, we could have them be picked up.
Does the BlueFS support the snapshot by itself?
Does BlueFS support snapshots? No, because BlueFS is just for backing RocksDB, and so it's just writing sequential files, reading random files. There's no rename. There's delete. That's about it. Like, it's just enough to run RocksDB and nothing more. Yeah.
Yeah, you mentioned about the OSD level, block level, and file level granularity for ratio codes. Mm-hmm. Do you also have anything much more granular, like chunk level?
Yeah, so all of those, the object block file interfaces are all built on top of Rados, and Rados has a set of primitive operations that support snapshotting. And it's actually on a per object granularity. So how you sort of expose that and package it up in a nice way depends on the pieces that sit on top. So RBD does it on a per image, per volume, virtual disk. CFFS does it on a directory basis. You can snapshot directories. Yeah.
Thank you.
All right. Thank you very much.